So it's kind of cute what happens. Our wave packet simply just marches along, and it kind of continuously goes over into this mathematical fiction zone, and it just disappears out of our system. We can also track this in terms of the trajectory that we've been discussing previously. And if I look at the trajectory of my particle, if I look at the position of the maximum location as a function of time t, like so, you'll notice I'm just moving along for time t less than 0. I start at negative values of x, and I simply head, this piece that I'm looking at, simply heads straight towards the origin and hits 0 location, if I'm tracking the maximum location, at exactly time t equals 0. So the trajectory looks something like this. It looks very much like the classical particle trajectory we were expecting. Now, the funny thing is, of course, we can continue on again into this no person's zone, right? So I'll draw that as a dashed line. We can continue to these positive values of x, which of course are just this, fictional location. So you can see we've at least managed so far to reproduce the first part of my claim regarding what the quantum system would do, and that is that it should begin by following this classical trajectory. The big question is going to be, well, what will come back out at us? Will it be something that comes back instantly, or it will experience a time delay before it comes back out? So this thing really is telling an interesting story, if you will. This packet that we have, this psi plus, is what we've been plotting so far. This psi plus function that we've been focused on seems to just go along into this mathematical fiction zone and disappear back in there. It's a little bit like these horror movies that you see, where behind the mirror, right, there's always this like imaginary place. I mean, is it real? Is it not? It's all very mysterious and mystical. And in these horror movies like Oculus, that was one we had a few years ago, right, you have to watch out. You never know what's happening. Sometimes, if you're not careful, you might actually get sucked into that mystery world behind the mirror. And that's what we're seeing happening here. But the other thing that can happen that you really have to worry about, especially in these horror movies, is that sometimes something can come from the Oculus, behind the Oculus, and come out into our real world and get us, right? So let's see what happens then with the other piece of my function. So the other piece of my function is this psi minus of x and t, right? And to analyze this piece of the function, that's the part that we've got right here that has to do with these terms. Once again, I'm going to use the method of stationary phase. And you'll see it has very familiar pieces to it, right? It's got some amplitude that's perfectly peaked here at k1 equals k0 again. That's fine. But now I have a new piece. I have this complex number I have to deal with. That then is multiplying a phase factor that's familiar to me, although it has an opposite sign. And then I have my usual time evolution. So what's happening with this extra piece all really depends on what is going on with this first complex number. So we better take a look at this complex number and think about it. So once again, for this, we're going to be looking at stationary phase for our analysis. And our focus is on that factor that you saw. It was K2 minus, it's K1 minus I alpha 2 divided by K1 plus I alpha 2. And this then is just some complex number, which I will call Z. And our job is to analyze this complex number in terms of its effect on the amplitude and phase of the overall function that I'm integrating here. So let's break it down into amplitude and phase. And as we all know, any complex number, conveniently, a generic complex number can always be written as a product of its magnitude, or amplitude, we might call it in physics, it's the same exact thing, times a phase factor, a complex phase factor, where the phase angle associated with my complex number is formally written as the argument of the complex number, or the arg of z. Very good. So let's take these one at a time. Let's begin by computing the amplitude of my of this factor. So the amplitude of my complex number, or the magnitude of the complex number, is I've got to take a magnitude of a ratio. But you will recall the magnitude of a ratio is the ratio of the magnitudes. So I'll have magnitude of k1 minus I alpha 2, and the ratio between that and the magnitude of k1 plus I alpha 2. And now we know how to take the magnitude of a complex number. It's just the Pythagorean thing, right? It's going to be square root of k1 squared plus then the imaginary part is minus alpha 2 quantity squared. But of course, when I square that minus sign, I don't get anything, so that's just a plus. Then divided by, here we have square root of k1 squared plus then the imaginary part alpha 2 squared. And you'll notice, of course, this is beautiful, right? The numerator and denominator are equal. The magnitude of this complex number is just 1. That's very nice. It's very nice, actually, for two different reasons. When we go back and look at our solution, the fact that this term has magnitude 1 does two very nice things for me. Okay, this ugly 2 has been bothering me. It does two very nice things. The first thing is that because this always has magnitude 1, it doesn't affect the overall magnitude or amplitude function, right? So I still have exactly the same amplitudes. So the peak will still be at k0. Nothing interesting will be happening on the amplitude portions of the complex number that I'm integrating. What's left, the other interesting thing that this has unit magnitude, is it kind of tells us that the magnitude of the reflected part that's coming back out at us with negative momentum is the same amplitude as we have of the incoming part. From a probability point of view, that seems to tell us that for every particle we send in, we're going to get a particle back, that there is a 100% probability that we will be reflected from that step, that we will be ejected from that forbidden zone. So those are the two things we can see from the amplitude. The phase now is what's really important, because that will determine for us our stationary phase and where our particle will be located. So let's look at then determining this phase angle, the arg of z. So the argument of a complex number, right, the phase angle will be, now this complex number is a ratio, so the argument of a ratio is, now it's not the ratio of the arguments, right, because the argument is going in the exponential. The argument, if you think about it, is a little bit like the logarithm of my function. And I know that the logarithm of a ratio is the difference of the logarithms. And the same thing is true for the phase angles. Another way to see this is, of course, you will remember when you multiply two complex numbers together, their phase angles add together. And when you divide them, their phase angles subtract. So the argument of a ratio is actually the difference of the arguments. So this will be arg of the numerator, which will be k1 minus I alpha 2 minus the argument or complex angle, or angle associated with the complex number k1 plus I alpha 2. Now to find these angles, I think we know what to do, right? We sketch our complex number in the complex plane. So we have an imaginary axis up here and a real axis down here. Both of my complex numbers have the same real part k1, so this length here is going to be k1 in both cases. And one of them is up by a distance alpha 2 in the imaginary direction, so this would be up by a distance alpha 2. The other one is exactly below it at a distance of alpha 2, but below the real axis. And then I'm interested in these angles with respect to the x-axis. So I'm interested in this angle here, theta, which, because these triangles have the same horizontal length, k1, I'm going to tidy this up a little bit. That got a little ugly. I apologize for that. Right, the length here is k1, and I'm interested in this angle, theta, which is the same as this angle, theta, because they have the same leg, k1, right, and they have equal but opposite direction distances alpha 2 along the imaginary directions. So if I look at this, the argument for k minus I alpha 2 will just be minus this angle because I always measure counterclockwise with respect to the real axis. So the first argument will be minus the theta in my diagram. And from that I have to subtract off the angle of this complex number, which is positive theta. So I subtract off positive theta. And the result is that I would get minus twice the angle theta. The big question is, what is that angle theta? Now, to determine the angle, of course, I've got this nice right triangle. It's got one leg is K1, right? It's a right angle triangle. The vertical leg is alpha 2. Oh, well, that should be familiar to me. I've seen that triangle before. That right triangle, when we go all the way back into our discussion, was, here he is. That right triangle has a hypotenuse equal to Q naught, which is a constant value. That's the beauty of this triangle and this Q naught. It's got a constant length for that hypotenuse, which is determined, remember, ultimately by the size of my potential step. So going back, I'm sorry for all the back and forth. I know there's a lot of math today. This is Q naught, like so. So the angle then I can determine, I could get it in terms of alpha 2, but alpha 2, remember, I'm doing everything implicitly as a function of K1. So I can get the angle better expressed in terms of constant Q naught and the constant K1. You can see then that the final conclusion here is that the argument of this particular complex number is minus twice, and the angle, the cosine of the angle, would be K1 over Q naught, so it's minus twice the arc cosine of K1 divided by Q naught. So now I think we're ready to write down the stationary phase condition. Condition for psi minus. So, once again, we need 0. We don't want the phase to be changing when we're adding up the largest vectors in the complex plane. So we want their derivative with respect to our label to give us 0, but we want to evaluate that at our peak amplitude, which, as we've just said, is the same as before. That peak is at K naught. And now in here, we have to write down the phase. Now, in this case, right, if I look at my factors, these first factors are just the amplitudes. The next thing I have is this, which has unit amplitude, but it has a phase that I've just worked out. So I have to put in the phase from this piece, minus twice that arc cosine. Then there will be another phase from this piece, will be minus K1x, not plus K1x, it's minus now. And then finally, I have the phase from the time-dependent piece. So there are 3 contributions to this phase. The first contribution was the phase angle associated with my complex number here. That's minus twice the arc cosine of K1 over Q naught. Then I had the phase from my minus K1x term, so there'll be minus K1 times x. And then finally I have the phase from my time-dependent parts, which is my usual minus h bar K1 squared on 2m times time t. That's a closed parentheses. And so now I think I'm ready to actually take this derivative. This derivative requires me actually to know the derivative of the arc cosine function. So we'll take a quick look at that, and then the rest of the derivative will be easy to take. I want you to notice if I have the derivative with respect to u of the arc cosine of u, to determine that, I can use a very handy trig identity. I want you to note something, right? That sine and cosine have those names because cosine is actually the sine of the complementary angle. It's the complementary sine. That means that if I have a parameter, and if I compare the arc sine of that parameter with the arc cosine of that parameter, I'm looking at 2 angles which are actually complements of each other. And the sum of the complements of an angle, sum of an angle with its own complement, they have to add up to 90 degrees, or pi over 2. So it's easy to get the derivative of cosine, arc cosine, if I know the derivative of arc sine. This will specifically equal the u derivative of arc cosine is pi on 2 minus arc sine. So that'll be pi on 2 minus the arc sine of u, right? And so the derivative will be just minus the derivative of the arc sine function, because pi on 2 just gives me a constant. And the derivative of the arc sine function is something that I think most of us remember. So I get this overall minus sign, and then derivative of arc sine is 1 over the square root of 1 minus the argument u squared. Perfect. So now I can write down the value for this condition. So the value for this condition then is going to be the k derivative of this business here is going to be minus twice. Then I have to take the derivative of the arc cosine of k1 over q naught. So the derivative of arc cosine gives me this function. That will give me a minus 1 over, but there'll be some extra factors, so I'll just leave the 1 on top, square root of 1 minus the argument squared, and the argument was k1 on q naught. That is squared. So that's the derivative of arc cosine, but it's chain rule. I have to also take the derivative of the insides with respect to k1, which gives me a factor of 1 over q naught. And all that gives me the derivative of my first piece, right? And don't forget, this has to be evaluated, of course, at k1 equals k naught. That's the first piece. Second piece, derivative with respect to k1 of k1x. That's easy. That's just minus x. That's no big deal. And then the final piece has a very similar derivative as before. It's h bar times 1 factor of k, that's k1, over m, because the factor of 2 comes down, times t. And again, this term is evaluated at my peak location, where k1 equals k naught. So now I think we can continue solving this. We can simplify my first term a little bit, I think, right? We can get rid of these minus signs. The other nice thing is you will notice I can bring my q naught into here. So this then is going to equal a factor of 2 on top. When I bring my q naught into the inside portions, that will be the q naught goes inside the square root, it picks up a squared. That will be q naught squared minus k1 squared, right? Again, evaluated for the particular value k1 equals k naught, minus x. And this term, when I substitute k naught for k1, that gives me h bar k naught over m times t. And of course, this we recognize as before. That's my incoming momentum over my mass. In other words, just my incoming velocity. Now, let's see here. One more step in simplification. This also looks familiar. Root of q squared minus k1 squared. You will notice that that square root, I know I've seen that before when I made my choice of parameters. Square root of q naught squared minus k1 squared, that is just alpha 2, evaluated at my value of k, right? So that will equal then, this then will become, this piece I've just recognized is alpha 2, and it's evaluated at the wave vector value for k1, and we're substituting in k naught for k1. So that's just my exponential decay factor, alpha 2, determined for my incoming wave vector k naught. So that gives us then our final result after all this work. The maximum location for my minus contribution to my packet is going to equal, well, I just move x to the other side of the equation, and I have two terms. The first thing is this interesting factor, 2 over alpha 2 at k naught. That's very interesting and suggestive. Minus then v naught times t. So you will notice it's just some constant minus v naught t. So this piece is definitely traveling backwards for us. So now I think we can complete our storyboard. To complete the storyboard, right, notice what I was plotting here for this peak here, this was my psi plus peak. I'm just going to keep writing that as psi plus. Psi plus is over here. Now for psi minus, when time is much less than 0, because I'm now traveling with a negative velocity, if I put a large negative value for time, I will be at a very large positive value for x. So in that case, my peak, my psi minus peak, will be somewhere over here. And you can see it's definitely on the other side of this, it's in this, again, this no person's land. At time t equals 0, I am actually moving closer in because I'm traveling with this negative velocity. But the location I'm centered at is not at 0. It's at this 2 over alpha 2 location. So it's going to actually be somewhere here. This is my psi minus. And the distance it's separated is by 2 over alpha 2, which is kind of interesting. And so you see I'm definitely moving here off to the left. Now finally, at large positive times, this peak will actually be at large negative, because it's a negative velocity, large negative locations. And the peak then, the minus peak, will now appear. And so it has come out of, from behind the imaginary zone into reality. So when we look at the movie sequence that we've storyboarded, we just see this packet going into the forbidden zone and then another packet coming out of the forbidden zone. It's kind of exactly what we were talking about with this quantum tunneling. If we now want to plot the trajectory to finish off our picture, you will notice we are traveling here with a negative velocity. So I'll have a slope that's negative of velocity, but it has a positive value added to it. So I'm going to have definitely the minus velocity, so I come down just like I would have expected with a equal but opposite slope. But I have to add a positive value to this line. So let me try to sketch that. If I can get the slope right, it's going to look something like this. Right? Here it is in the no man's land, no person's land. Then it comes out here into reality. Right? So you can see that indeed what I have seems to be delayed in time by what I would have expected. This is the classical trajectory I would have expected. I'm actually am going to come out later at some later time with some time delay delta t, which reflects exactly how much time this packet has spent in that forbidden region. So just to wrap up, let's compute that delta t and see if we can make some sense out of it. To compute it, I can simply rewrite my x max. I could write this as minus v naught times some time t. And I'm going to pull this piece here into parentheses. So I have t. I need a minus sign, so minus and minus gives me a plus. And then what I need is my factor of 2 over alpha 2 on top, divided then by the v naught that I've factored out. So you can see this is exactly minus vt. This is the backward traveling packet I would expect, but it doesn't occur at the normal time t. It has a delay to it, and this is my delay time, delta t. Then has this interesting interpretation. It's twice 1 over alpha 2 divided by my velocity. Now, if I want to interpret that physically, that's kind of neat, right? It says, well, if I'm traveling at velocity v naught, the time it would take me to travel 2 times 1 over alpha 2 is the effective distance I've traveled divided by my velocity gives me my time delay. And why would I think I should travel a distance twice 1 over alpha 2? Well, this is really neat because that information is essentially buried in the other portion of my solution. The x greater than 0 portion of my solution over here, right, has this decaying exponential with a decay constant alpha 2. And as we had commented at the very beginning, with a decay constant of alpha 2, the length scale, 1 over alpha 2, is exactly the exponential decay length. So it's just as though my packet has traveled in one decay length, one distance of 1 over alpha 2, and then traveled back that distance for a total distance of 2 over alpha 2, and it traversed those distances with a velocity v naught. That would lead me then exactly as a physical interpretation to the time delay that we've experienced. So I hope you can see that all of this really just comes from being very careful, but simply solving the time-dependent Schrodinger equation has built within it this entire beautiful storyboard of the collision between an incoming packet and a step in the potential. And that wraps up our discussion of this problem.